All right, good morning, everybody. Thank you for joining us. Good afternoon for some. This is Jeff Creighton with Flow Control, and I have Alicia Clark with me as well. And we're happy to share this webinar that we've been working on for a while. We've had a chance to share it with a few people already, but I think it's good information that we'll show some of what we've been working on over the last couple years and hopefully provide some new insight into the things that we're doing. A couple things to start with. We will be recording the webinar, so we'll be able to share that with you, and you can pass it along to others at the end of the session if they weren't able to attend today. We'll have everybody on a listen-only mode, so if you do have questions, please click the raise your hand button or feel free to type in the chat and we'll address those. We'll try and save time at the end to address those together, even if something comes up throughout the presentation. But we will hold time for that, and we should be able to get through here in less than an hour is our goal to get this out and have time for discussion and get everybody on their way for the rest of the day. So thank you again for joining us, and we'll go ahead and get started. What we wanted to share with everyone is a little bit of the idea behind data. There's a lot of companies and facilities and locations, and everybody's talking about data. And one of the big things for us is putting that data to use and really making it relevant and actionable. And that has to do with putting it into context. And that really ties into efficiency at the same time. And so we want to be able to put those two together. So how do we do that? Where do we start when we go with that? We talk a lot about chilled water systems. And when we look at a system, it really has that one purpose, which is all of the parts and pieces have to work together to move heat throughout our buildings, throughout our facilities and our campuses. That gives us lots of different opportunities when we're looking at how to address efficiency. There are a lot of components, there's different configurations, there's different sequences of operation, there's lots of things that we can do to address efficiency overall. And when we look at this kind of typical schematic, it sort of puts everything on a level playing field, right? But the way that we view it individually sort of tilts it towards what we know and what we understand. So how do we gain a broader understanding of that entire system? Well, data can help us to guide our focus and to guide that conversation. So what sort of data can we use, right? We have facilities that run the gamut. You have places that have no data to places that have too much data. And really either one of those can be paralyzing, right? More data may be more resolution, but it doesn't always mean that it's better, right? It also adds complexity, not necessarily clarity. So we want to be able to take all the different pieces that we can use and use them selectively, right? Some places will start with just purely, anecdotes or equipment logs, things like an operator telling us that they turn on the second chiller when it's 80 degrees outside, or this particular building is always uncomfortable, things like that. Then the next level is some sort of an automation system trend data. Maybe we have metering capabilities at the building level or at the plant level. Maybe we go all the way out into the air handlers or into the spaces. We tend to roll those up into some sort of an efficiency. Maybe it's a plant efficiency in terms of kW per ton, or we might put those into different metrics like a load profile that gives us some perspective about how does that system operate under some different conditions, right? One of these things, all of these things can be useful, but one of the shortfalls is they really tell us what performance is or what it was. It doesn't necessarily tell us what is it supposed to be. How should our systems be responding under these conditions, under these loads, under these, different operating profiles. So we need to set some expectations so that we can start to build that benchmark and start to guide our operation and our perspective, right? So if we take a different look at that same schematic, you know, all we do is we take it and we tilt it, right? What drives the way that these systems are built and operated? Well, they all depend upon each other. They're all still connected. But really, that heat transfer starts that design. It starts from the coil, because that is the purpose of the system, is to remove the heat from the space, right? So if that is driving that entire design, a certain, you know, coil selection for certain BTUs is dictated by the supply water temperatures, the design discharge air temperature, the coil delta T. So all of that is going to dictate the rest of that system. That certain amount of flow required at the coil dictates the pipe sizes. The operation dictates the controls. The amount of flow across that entire campus or building dictates the size of the pumps and the chillers and the BTUs. So all of that depends on what's at the top of that pyramid, right? Those coils drive the entire system. What happens if we have some sort of an inefficiency in that, whether it's you know, improper calculations or maybe some over design or some poor performance? Well, anything that happens at the top drives a larger requirement all the way out, you know, throughout that foundation, right? If we have poor performance at the coil, then we need bigger pipes, we need bigger pumps, we need bigger chillers, right? That whole foundation has to support that heat transfer process. So it becomes really critical to get that design and that operation correct from the top, so that we don't build in additional cost in the entire system, you know, from the start or throughout the operation. So we wanted to go back to that data and say, how does that help us, you know, evaluate the performance? What can we learn from it? How do we take that and use it to move forward? We looked at 3 different projects that we executed in different facility types and different climates. We looked at a clinical research center outside of Los Angeles, California, a college campus in Yuma, Arizona, and a university dental school in Kansas City, Missouri. 3 fairly different climates, different uses, a couple of them campus type facilities. The dental school is actually a single building. All of these projects were implemented by our sister company, by Flow Energy, between 2014 and 2015, completed in that period. And we've actually looked at the last 2 full years of operational data, so 2016 through the end of 2017. And we looked at data from our smart valves that we installed at the air handler cooling coils. So we captured 1-minute interval data on the air side and the water side. So we looked at leaving air temperatures, return air temperatures and humidities, entering and leaving water temperatures, flow rates, inlet, intermediate, and outlet pressures, all captured at the DeltaP smart valves that we installed at each individual air handler. And we were able to roll all of that up and look at it in a couple different ways. And we really wanted to find out, you know, what does that tell us? What does 2 years worth of data tell us? We have a lot of our design and our information in the industry built around design conditions. But as we've all talked about for years, that's not the way that the systems tend to operate. So when we look at that over that 2-year period, what can we find, and how does that influence our decisions? So we started with a simple metric. We wanted to look at delta T initially, because that is one of the terms that we talk about a lot. We use that as a metric for design and for operation. It's kind of a benchmark. So in our California hospital, here's one of the coils that we investigated here. So this is a research lab, about 15,000 CFM, about 50% outside air minimum, and a 73-ton design, a little over 100 GPM. A 16-degree design delta T. with a 48-degree discharge error on that coil. Those are all of the design parameters for the coil selection. When we look at the actual operating data from that coil, this is the profile that we see. Here's our design delta T way down here on the left, and our average delta T then is operating about 32 degrees over the 2-year period in cooling operations. So when that chilled water valve is open, we see that we average about 55% load on that coil, just under 30 gallons a minute on a coil designed for almost 110. And again, a 32-degree delta T on a coil designed for 16 degrees. Okay, is that an anomaly? Well, we'll keep looking at the other facilities as well, right? So in Arizona, we see a very different profile in terms of the usage on this one. This one is for a classroom, so that probably drives a lot of the profile, whether that's occupied or not, whether we have students in the classroom, schedules, summer and winter schedules as well, right? 19,000 CFM, about a 30% outside air minimum, slightly bigger coil, but a lower delta T on the design, a 10-degree design delta T on this coil. But again, we see an average delta T over that 2-year period at 26 degrees. So 2.5 times the design delta T is our average condition, operating well below our peak load here, averaging 13% load, 11.4 GPM on a coil design for 206 GPM. So again, that could tell us, is that significantly oversized? Is this a fluke? But we're starting to see our trend here. When we look in the Missouri coil, medical office building here, 15,000 CFM, 62 ton, 150 GPM, another coil designed for 10-degree delta T, and we see on this one about a 14-degree delta T average, again about 30% load. So when we start to look at all of those different facilities, the different space types, the one thing that really stands out is that they average well below our design load condition and well above our design delta T condition. As far as space types and regions, we know that the Missouri campus is certainly going to have a little bit more humidity to deal with than either the California site or the Arizona site. So that certainly impacts the performance over time, but we also see that they all operate, significantly at part load conditions. So that delta T metric is great, but it really doesn't tell us the whole story. It only tells us a very small part. And the main reason for that is delta T is a result, right? It is a side effect of the control and the different parameters that go into that, the water temperatures, the air temperatures, the flow rates. So it is just one metric that we can use for evaluation. So if we take that and we look at it in a different perspective, we can look at load versus flow. That gives us a little bit more insight into how that coil is actually performing. So for that California coil, when we look at that here, we'll look at percent load versus percent maximum flow rate. So on this one, we see, it gives us some idea of the effectiveness. Well, on the y-axis here, we have percent load. So we actually see that this coil gets up to the peak load conditions under some operating scenarios. However, it only operates up to about maybe 60%, 65% of the design flow. So we overlay that graphic that we've seen a lot of times through ASHRAE. It's that ARI curve for a cooling coil. Our main dotted line here tells us the design delta T. If we're to the left of that, that's better than design. If we're to the right of that, that's below design. That ARI curve tells us the ideal performance there. Well, we see that we're operating well to the left of even that ARI curve. So what is that telling us? Well, does it mean this coil is drastically oversized? If we look at the load, we see that that's probably not the case because we actually get up to 100% load on this coil. So what is it that's driving that coil to operate beyond the expectation, beyond essentially the ideal performance for that curve? What are the other influencers that go into coil operation. So this is a big part of why delta T alone doesn't tell us the whole story. So one of the influencers comes from the water side, specifically the entering water temperature. So that has a big impact on how much capacity we can deliver from the coil and how much water we need to deliver that capacity. So for example, every 1 degree Fahrenheit drop in the entering water temperature to a coil, we actually expect to see about 1/3 of a degree increase in the leaving water temperature for the same discharge air. So that tells us not only do we increase the delta T on the entering water side, but we also expect it to increase on the leaving water side. So that can be really beneficial. If we look at this particular coil here, we have a design entering water temperature of 40 degrees, design delta T of 16 degrees, and we see that as that entering water temperature drops, as we go to the left on the x-axis here, the leaving water temperature also increases and the delta T increases dramatically, right? We follow a pretty linear trend on that case. Another thing that really impacts performance is the flow stability. So we know that as flow rates are more stable, more constant, or consistent, that we know that heat transfer improves in the coil. The other thing that impacts that is the design delta T of that coil. So a coil with a higher delta T design, say a 16 degree or an 18 degree design over a 10 or a 12, becomes more sensitive to stability, to flow changes. Because if we look at that flow versus load graphic again, you see we still have that same y-axis, we still have the same amount of capacity, we just have less flow to manage that capacity, to provide that capacity with a higher delta T. So that means for every change in flow, we have a higher change in load. So it becomes more sensitive and stability becomes more critical with high delta T's. On the air side, there's another impact there as well, right? So entering water temperature is probably the biggest impact on the water side. Leaving air temperature is probably the biggest impact on the air side. And if you think about a coil and the way a counterflow coil is configured, those two parameters, entering water temperature and leaving air temperature, are right next to each other on the outlet of the coil. So that's why they have such a big driving influence. So for every degree increase in leaving air temperature, we also expect to see about a degree increase in leaving water temperature. So that is also going to increase our delta T. We see that for this coil with a 51 degree design leaving air temp and a 10 degree delta T design, as the leaving air temperature increases, we see delta T continues to increase as well. Again, higher delta T, coils have more sensitivity to changes in the airflow or changes in the air temperatures, as well as airflow volume and velocity. That also impacts our performance. Configurations as well. Blow-through versus draw-through configurations for a coil in relation to the fan. A draw-through coil has to actually lower the discharge air temperature off of the coil a little bit below what you would get on a blow-through configuration. So there's slightly higher latent cooling, slightly lower discharge air temperatures. So that can weigh into how much flow we need and actually how much load we have to do in the system. Outside air percentages also impact our performance, as does the region, as we'll see between the Arizona, California, and Missouri locations. So if we go back to that load versus flow graphic, and we filter out a bunch of those parameters where we're operating outside of that design expectation, right? So we narrow it down to look at only conditions where the entering water temperature and the leaving air temperature are within plus or minus 2 degrees Fahrenheit of the coil design. So we're not, we're still looking at the full range of load and that operation. We're just trying to narrow it down to say, how does that coil perform under some more controlled conditions? So the first thing that shows up, we have a little bit smaller data set here, but we're still operating well above that design delta T. Closer now to that ARI curve, so that makes sense that we're putting that coil back into its expected parameters of operation. Less runtime, but it still operates well above the design condition. So again, why do we lose so much of that operating time? Why do we lose so many data points when we start to filter that out? Well, we spend a lot of time operating these systems, number one, not at design, but we also have resets built into these systems. And a lot of those are built in based on code requirements. So discharge air is a really good example where the coil is designed and selected for a 48-degree discharge air temperature, way down here on the left-hand side of this graph. And I realize the axis is relatively small here, so it might be a little difficult to see on a large screen. The average operating discharge air temperature on this coil is actually 53 degrees. So we spend so much more time operating above the design in this case. That's a big influence on the total operation. And that goes into place generally based on code. Maybe it's a discharge air reset on outside air temperature. Maybe it's on a load. Maybe it's on a return air temperature. But that's very common across a lot of facilities. On the entering water temperature, we also see a reset. In this case, this maybe is not as common. We have a 40-degree design water for this coil, and this facility actually resets down. And so we see colder entering water to that coil, whereas a lot of facilities tend to operate the other way, and they may reset the water temperature up. But as we saw earlier, water temperature has a big impact on coil performance. So as we reset up, that requires more flow, and that is detrimental to our operating delta T. So if we go back to those individual coils that we looked at before, we want to take a look at them and say, how do those design parameters, how does that impact our view of it, right? So in California, on that research lab, we averaged a 32-degree delta T over that entire operating period. When we filter that down and we narrow it to within 2 degrees of our design leaving air temperature and entering water temperature, what do we see? We see it's about 50% or 56% load, so very similar to the operating conditions across that entire 2-year period. A slightly higher flow rate, 39, almost 40 GPM, and a little bit lower delta T, but still at 24 degrees on a coil designed for 16-degree delta T. We're averaging 39-degree in water temperature and 49-degree leaving air. So a smaller data set, but we're still at 150% of our delta T design. In Arizona, we'll take that same perspective here, and in this case, we actually have a really, really small data set for conditions when it operates at design or closer to design parameters, right? But it's a little higher load, so 27% of the design load as opposed to 13%. A little higher flow rate and about 15-degree delta T. Again, 1.5 times the coil design. So one of the things that actually makes sense with this is that we expect to see a little higher load condition when we bring that coil closer to the expected, I would say, design conditions, right? So as you get a higher load, more often than not, you'll see lower discharge air temperatures and you'll see colder entering water temperatures to those coils. So that lines up with our typical operating scenarios and strategies there. When we look at the last one in Kansas City, we actually see something a little bit different in this case. And that is a fairly big data set with those conditions, meaning that there are either fewer resets or fewer opportunities to reset on this coil. And the other thing that we see is that the average delta T actually goes up when we look at conditions where they operate closer to the design leaving air and design entering water temperature. The red highlighted components here that we see on both of these graphics, the previous one and the new one, are when they're operating that coil below the design discharge air temperature. So that has an impact on the delta T. When we look at it and we narrow that window to operate closer to design discharge air, that raises our delta T in this case. And again, the thing that starts to line up here on all three of these coils, we see that with those conditions, we expect to see about 150%, 1.5 times the design delta T. So this really lines up with our philosophy that design delta T is really good for one thing, for design conditions. When we start to look at the operation over the course of any sort of part load, over the course of any time period, we expect that that delta T should be exceeding design all the time. And we really want to see that essentially as a new benchmark or as a new metric, right, when we do our evaluation. So putting all of this stuff together here, looking at these three different campuses and multiple coils here, what are some of the things that we find? We find that most coils are oversized. Some of them do reach their design capacity, and that depends on the utilization. We tend to see that more often on things like surgery, maybe 100% outside air research units, things that don't have as much flexibility in their operation, but most of them are oversized. And when we take advantage of the coils that are oversized and recover that capacity, we're actually able to redeploy that. So in Arizona and in California, both of those campuses recovered close to 25% of capacity, meaning that they were actually able to not only shut off operating chillers, but they were able to add load, able to build new buildings and add those to the existing loop without adding any additional chillers. So previously they were running all of the equipment. They didn't have the capacity to supply new cooling. And after these projects, they were able to go out and provide that capacity using the existing infrastructure. So a big impact in as far as total infrastructure costs. In California, on that campus, they actually drive the entering water temperature down below the design conditions on purpose. And so that was actually in place before we got involved with this particular project. And the reason they did that was that allowed them to get water further out into the system and actually serve more physical buildings because of the pumping limitations. So with that colder water, they were able to supply more of the campus. It did mean that they had to run more chillers and essentially all of their chillers to do that, but they had the capacity in the plant to do that. So after our project, we actually were able to cut down that flow rate by essentially doubling the delta T on that campus, such that they were able to shut off all of their building pumps, and they continued to run that cold water because that allowed them to run without those building pumps. So they recovered some of that capacity. They were able to shut off one of their chillers, continue that same operating strategy, but doing it more efficiently overall. The other thing that comes out here, and this was a big factor on the Arizona campus, is that performance, when you have this information now in terms of delta T and an expectation for operating performance, it can be used as an early warning, really indicating potential comfort issues. When you see that delta T or leaving water temperatures start to drop, that's an indicator that there's something wrong with the leaving air temperature initially, or there's not enough flow, or there's too much flow, or things like that that start to stand out. And we can capture that performance impact much faster than we can see an impact or get feedback from a tenant in a space, because it does take time for that air temperature to change, for that tenant or that occupant to perceive that, right? So performance is really a good indicator when you have that expectation of this is what it's supposed to be. So putting this together, what are our expectations? Well, the number one thing is that we should see coils exceed design delta T, right? Regardless of location or service. So we looked at humid climates, dry climates, temperate or sort of a mixed climate in California, and all three of them operate very similarly, right? We see that expectation of 150%, 1.5 times the coil design delta T. So really, when we take that expectation of a design parameter, we need to put that in the context of how should it be operating, right? So that means that we need to start setting part load performance targets. Design is for design. That's great for that one condition, but the rest of the time, we need to reset our expectations and start to give ourselves new targets, right? If we look at anything else in a central plant, if we look at a chiller, you would never take that chiller operating kW per ton at design and use that as your expectation for the total, IPLV or total seasonal efficiency, right? We have a chiller part load coil, or a part load efficiency curve. We have part load expectations for pump variable frequency drives. We never take that peak load performance and say that this is the only variable that we have, this is our only metric, right? So if that chilled water coil, we put that at the top of the period, and that's what's going to drive, or the top of that pyramid, and that's what's going to drive the rest of our system design and operation, we need to start setting different expectations for performance. We can't pick that one metric and say that that's good enough. We need to start looking at it in terms of what should it be and how do I get that operation out of the system, because that is going to dictate the rest of my system. And that data then, that's what helps us to make sure we stay on top of that, right? It's very useful for troubleshooting, for operation, for new designs, when it's in context. So we need to have the metrics around it to tell us, is this what it's supposed to be? If I've reset my discharge air temperatures or my water temperatures or my airflows, how does that impact my total performance, right? There are a lot of variables that go into that coil performance. So we need to be able to take that information and use it in the right format, right? We know that there are a few big influencers on the way that coil operates, but the control side of it, that control valve in particular, becomes a really big factor in determining the total outcome, right? We take all of these inputs in there, and we have to deal with that flow to deliver the right discharge air temperature to provide the comfortable environment, right? And if we do that correctly, then we start to see the benefits, we start to see the side effects, the higher delta T's and the lower flow rates in total operation. Once we get that stable control, that helps us to evaluate and initiate some of those smart resets. So it might be that we really need to reset our entering water temperature to the coil. We need to reset those down because there's a big benefit to that in terms of how much water we need to provide throughout that system. There are cases where we could go the opposite direction, maybe under really low loads when we have minimum flow conditions. So, but once you get that stability and get that data side put together, then you're able to manage those correctly and have some really good feedback in terms of what makes sense. But it all comes back to that coil driving that system performance and really maximizing the efficiency there so that we can provide that segue into the other complementary measures. We can take advantage of our variable frequency drives, our variable speed chillers, our resets, our total plant optimization and efficiency strategy. But all of that has to work together. And if we don't address that heat transfer at the coil first, we're never going to get that full, maximum efficiency out of the coils. So I know we put a lot of stuff together there, but we were excited to get some of this information out in front of you and really kind of open it up for some feedback and further discussion in terms of, how can we take this information further? How can we use that to benefit both existing facilities and new facilities and implement that, the right way so that we can take advantage of that. We can make these systems operate the way that, we know that the potential is out there when we get that information and we can get that into the right format for discussion. So with that, we'll certainly open that up to questions, and hopefully feel free to type those in the chat box. It's probably the best way to get any feedback, and we'll go from there. So there's a question on how did we get such low entering water temperatures in the California coil, and that was just driven by the chiller operators. So they actually typically run with very low entering water temperatures, and they actually run thermal storage as well, and that was just something that we recorded, and we actually looked at that across several coils just to verify that it was not a sensor error or anything like that, but they do physically drive that water temperature down, and it just means that they run typically more chillers to do that, and there is an efficiency component or factor when you run colder water temperatures, but the way they're justifying that is not running the building pumps, and actually being able to provide capacity further out into the system that they would have been able to achieve with warmer water temperatures. Another question about, do we look at fan kilowatt energy as leaving air temperature was increased? So one of the things that actually showed up on the Arizona campus, one of the buildings that was struggling when they were not getting enough cooling, the impact of that was leaving air temperatures were high. And because they were not providing enough cooling, that building, the fans were running really hard and adding a lot of energy consumption to the building. So when we actually got water temperatures where they needed to be, and we actually got cooling out there, they were still able to do resets, but we saw about almost a 25% reduction in electrical energy in one of the buildings alone because of the fan impact. So getting that cooling had a huge impact on the fan side. A question about what kind of control technology are we using? So all of these projects, we're using our DeltaP smart valve and our flow energy surge platform for monitoring and information and insights around the energy consumption. We integrated in with the existing control systems, so we actually worked with Siemens on one of the campuses, an Allerton system on another one, and a Honeywell system on a third one. So we're really control system agnostic. We were able to integrate with each of those. Some of the cases we actually operate with some of our own local control strategies where they had some issues with their existing control systems, but the majority of these are operating under the same control strategy, leaving air temperature, discharge air control, using our DeltaP smart valves to provide that stability with the additional instrumentation that we're getting from the smart valve. So a question about, what conclusion do we draw from the information about proper coil sizing? One of the things that we get into is that, we mentioned coils are typically oversized. So there's always a concern about safety factor on coils. And one of the ways that sometimes we can get around that is to provide colder entering water temperature to a coil. So if we're a little bit less conservative, I guess, or a little bit more accurate on the coil sizing based on the load, we know that we can always get more capacity out of a coil with colder entering water temperature. So if that's an option, that does give us some flexibility in terms of how we size our systems, right? We know that we should have diversity built into our systems as well. And so based on that total sort of collective design and that collective sizing around the chillers and the coils, there's usually that capacity to provide a little additional capacity out of the plant and take advantage of that at the coils. We can also see that in terms of maybe sizing in the piping and the pumping, sizing for a little higher velocities there, and we could also carry that through into the coils as well. sizing with a little higher velocities on the tubes and the coils could be an impact as well, where we actually make the coils a little bit smaller and save some first cost there, and still get the advantage of operation over the entire part load performance. A question about, do we look at the compressor energy as the entering water temperature was reduced? So we did not specifically look at that, but what we did look at was the total campus energy consumption. So that particular campus in California, the project baseline, we had an expectation of saving about 4 million kilowatt hours a year. And the measured results at the end of that project were closer to 6 million kilowatt hours, with a significant reduction in total demand as well. So even with the additional chiller consumption by providing colder entering water temperature to the coils, we still saw a much bigger impact by the total reduction in flow, and actually, turning off a chiller itself was able to provide a bigger benefit in terms of the demand and the overall consumption. Those are some good questions there. We're certainly will be open for more questions too. We'll also be sending out a recording of this, so you'll have a chance to review it, take a look at some of the graphics again, or share it with other folks. And if something else comes up, feel free to reach out and let us know if you have any additional questions. And we hope to get some more feedback with this as we continue to put this stuff together. It's always really interesting for us to get a chance to go back and really dive into how these systems operate. And one of the big things that we've done with our smart valve platform and with the surge platform is really tried to pull that information out of the system. So a lot of systems, we spend a little bit of time up front with commissioning and a quick functional test to verify performance, but once it goes into operation, it's really hard to tell how it continues to operate. And so it was really nice for us to get a look at it and say that, yeah, 2 years after installation, 3 years in some cases, we're still continuing to see that operating performance. And that is important to us, is that we should be, designing around that part load performance expectation, but we should also be able to sustain that. We need those savings to persist, and this is a really good way for us to check back in and make sure that they are continuing to operate the way we expected to see. So I think with that, with no further questions, we'll go ahead and wrap it up. And again, feel free to let us know if we have some more questions. But appreciate everybody joining us today and taking a little bit of time out to join the webinar, and hope it was useful information. Have a great afternoon, everyone.